introduce you, and then you can, and then you can, share screen. You can do it from your end, yeah. If that's okay with you. I mean,
yeah. Yep.
Yeah. Okay. So welcome everyone to the Healthy Planet Action Coalition meeting, our general meeting, and we're very pleased to have Alan Gadian, who is a senior scientist at the National Center for Atmospheric Science and a visiting professor of meteorology or dynamical meteorology. I'm not at the University of Leeds, and is working with many folks here that many of you know, like Stephen Salter and Robert Tulip and Herb, and I don't know if Rebecca's here, Brian von Herzen. They're working on, moving forward the marine cloud brightening technology that we and many others believe is a very promising direct climate cooling method, potentially a very promising direct climate cooling method that should be really investigated and researched and piloted if things turn out the way we think they might as soon as possible. So anyway, I'm not going to stop editorializing. So Alan, without further ado, if you want to just we're gonna do a presentation. Alan will go for about 45 minutes, and then we'll have about 45 minutes of discussion. And we want to end promptly at it would be 6 o'clock Eastern Standard Time where I am right now, because Alan does have some other it's quite late actually in the UK for one thing, and it would be not fair to go much longer than that. So okay, Alan, take it away, please. Thank you.
Right, I shall try and share the screen. Just a minute.
I'm sorry. Let me just add, for those who are new to the Healthy Planet Action Group, please put your email in the chat if you want to be on our mailing list. We've had, numerous, I think, very interesting talks, and many, a good many of them are up on the website. We're trying to get the other ones up there right now, and some papers and letters and other things that. And we would really welcome, your participation at our general meetings, which are held once a month usually at this time, Thursdays. Well, it's actually twice a month, alternate Thursdays every month. Okay, so sorry about that, Alan. Go ahead. Yeah.
No, it's okay. Can you see that screen? Is there anything wrong? Everything's fine. Right. Yeah. So 12 quick slides on introduction. I decided to include them because it means that I can then move faster with the other slides. So, right. So basic problem. So I've just given 5 quotes. The bottom one from the EU that came out very recently said these SSTs we've had are unprecedented and beyond the extreme. There's other papers I've listed there, the work of the UK Met Office, obviously, because I've been influenced by the Met Office, which says that the UK climate's changing very rapidly. The WMO also says record levels of gases. The UK Parliament has also said something about this, and satellite data suggests that the global surface temperature is increasing by up to 0.34 and maybe 2 to 3 times more in the Arctic. So these are the background, which I think you all know. These 2 slides actually convinced a man called Boris Johnson in 20th of January that it's something he should be worried about. You've seen all this information before. Carbon dioxide increase, top left. Top right, the observed warming only over the space of 40 to 50 years at the top right. The global mean temperature differences, everyone's seen that, and the sea level rises. and that's been there. You've also probably seen the pictures on the left, which says these HADEX3 are actually changes in temperature extremes. And that's something I want to emphasize later. The extremes are the ones we're looking at. And if you look over large parts of South America and Europe, you're getting extreme temperatures well over 4 degrees Celsius already. On the left-hand side, the alarming thing is the number of days where the temperatures exceed the maximum percentile. But on the right-hand side is something that I really want to emphasize as well. Penn State University has come out with a new definition of comfort, if you like, or body breakdown. And that said that 100% humidity, 31 Celsius, which is a low 90s Fahrenheit, the body will shut down. Previously, it was put at 35 degrees Celsius. The figure is the old figure, which doesn't include these latest results. But the other point is temperatures above 40 degrees Celsius can cause grave issues with working computers, machinery, and with my other hat as advising the nuclear regulator on their $100 billion projects with nuclear power stations. This is the modeling equivalent. I think we are on RCP 8.5. What does that mean? That means the 8.5 means watts per square meter that we're going to have. I think we're on the right. I think we're destined for temperatures of 4 to 5 degrees, definitely. Doesn't include extremes. So this is a slide that I really want to, a background I want to emphasize mostly. So as long ago as 2007, IPCC gave the figures of carbon dioxide contribution, water vapor contribution, methane contribution. In 2010, Schmidt gave the figures that 50% of global warming came from water vapor and 67% if you take the clouds away on those regions that are not gone clouds. And then you look at CO2, that's 19%. And when you take the clouds away, 24%. But this below in red is the major issue that we've got to address. That this Clausius-Clapeyron is standard grade physics in the UK, and the saturated vapor pressure increases by 7% for every degree. So when you get up to 4 degrees Celsius, which we're going to get to at the present rate relatively soon, then you can see that we're going to get 30% of 50%. So we're going to get a huge contribution. So removing CO2, if you could do it tomorrow, great. But the problem with it is that you're not going to attack the problem of planet overheating. And on the right-hand side, I think I've given the data that in 2022, the 50 permits, maybe 3 gigawatts each. Greenpeace in 2022 said there were 9 gigawatts. India is going to increase its coal production by almost 30%. And the amount that's been removed globally is insignificant. So whatever one thinks, the planet is being cooked, but it's not that simple. And again, I referred to the Atlantic, that a paper has just come out saying that the Atlantic meridional circulation is on the verge of collapse. Best estimate 50 years, the authors say by 2025, but it's between 15 and 300 years, and it would change the whole of the North Atlantic, both sides of the North Atlantic and reduce by 4 to 10 degrees locally. You probably don't know where the Falklands are, but off South America, we're going to get typical weather, windy weather, and trees, well, they'll be a problem because they won't be able to stand upright. The other point is the Greenland ice sheet is now going. So when I say many oceanographers, there's an organization called the British Antarctic Survey, which has a station there, and over a pint of beer, she will tell you the Greenland ice sheet is now past the point of no return. Without doing serious work, it will not reform. And the Wikipedia gives you 1.4 meters. Oceanographers give you 7 meters. So whether you're living in Long Island or wherever, Florida Keys, and that's a reference to the paper, we're in trouble. Right, so that's the background. That's not controversial in my book. Okay, so now I want to now show you something that has happened this year and why it is encouraging. And I put the word, it's good news, and it isn't good news, of course, but scientifically, it's good news from my point of view. So why are the sea surface temperatures? If you look at the right-hand plot, you'll see that
somebody mute their, please mute if you're not Alan, sorry.
Yeah, okay. If you look at the right-hand plot, you'll see this significant black line, which was the June sea surface temperature in Northeast Atlantic, and that's really significant. You're talking about 1.5 degrees above minus 0.75. So you were really over 2. And the left-hand one shows the sea surface temperature anomalies in June, which is plus 1.36. This is all data. So on the right-hand side, we're going from the 1970s to the 2020s. Okay, so why has this happened? And people will talk about the El Nino, which hasn't happened yet, so that's going to make further problems. Saharan dust, possibly. Anomalous high pressure over the Azores Islands. Well, yes, that is true. But the significant thing, I think, or one of the significant, it's all of them, is the reduction in sulfur emissions from international shipping. And you can see this is a graphic from Carbon Brief. And we all know about this, that this has, over the space of a year or two, has actually caused this effect. It's global. The effect is global. And this is really one of the most significant things. If you look at the left-hand plot, there's peaks usually in March, and here, the 60 south to 60 north, it's in August. We're talking about hugely significant. This is the mean here, and that is 2 standard deviations. So we're well out of 3 standard deviations here, 95%. Now, I want to point out this area here, and these areas here. And with temperatures up to 10 degrees off Newfoundland, it was easy to predict that a hurricane would land on those shores. And this is the reason it's encouraging, is because it gives support to the idea that varying the aerosol or the reflective power in the lower atmosphere will affect the climate. Now, Bjorn Stevens, who runs Max Planck, when I first presented this to him, he stated, this is a lovely fairy tale, and I told him there's a lot of truth in fairy tales, but this was 10, 12 years ago, and I presented what was happening, and I think he would now support it. But what I'm going to talk about with marine cloud brightening is this area here. Now, a lot of people use the average incoming solar radiation, 342 watts. I prefer to think of it as 1360 watts because that is the figure at midday. And what happens is some of this radiation is getting reflected back. And if you go off the coast of South America, Chile, you'll see that the copper smelters, which are 2,000 meters, have actually reduced some of the stratus clouds. And I'm going to show you a picture. So this is what we're talking about. We're talking about this yellow bit. So I'm not going to talk about stratospheric aerosols, but I'm just going to talk about what I think is the optional system. But before I do this, these are the things that are being suggested. Slide from Rob Wood: space-based methods, stratospheric aerosols, decreasing the amount of high-level cirrus. Some people say that when 9/11 occurred, there was less cirrus and it affected it. Surface albedo enhancement, well, I don't think that's viable. And this marine cloud brightening here, and this is to me the safest, and I think a lot of you agree with that. So now we're going on to marine cloud brightening. So what happened was Toomey in 1974 said that aerosols will lead to more aerosols or more smaller particles will affect the reflectance. And if you take if you take two clouds as we see them here, the same amount of water, equivalent water mass, and you make them smaller, they have higher albedo. And this was started by, this then went on to Latham in 92, and it followed Slingo, who first applied it to clouds in 1990. Tony Slingo, unfortunately, died. So this is a project I went on in about 2008 off the coast of South America, Chile and Peru. And this is, there's a little yellow ship there, well, a buoy, and we made measurements there. And this is a quick cycle through. Rob Wood led the project, and essentially stratocumulus cover more than 30% of the oceans. And I wanted, when we did the work, we focused just on some of those areas, 10% of the ocean surface. A lot of smaller drops produce whiter clouds, and we went out to Peru and measured these clouds. Now, it might seem amazing, but this was the first real time. There was a DICOMs where they did it off North America, but this was the first time we'd really done it with 4-5 aircraft from France, UK, 2 from the US, and 1 from Portugal. And this is what we're talking about. And over here, I've stolen Stephen Salter's slide here, and you'll see these are glass beads, and these are the shape of this is the scaling of the albedo. And what you can see is that the mass of glass is the same in both these jars, but these have different sizes. And we've actually, Stephen's exaggerated it, but so you can actually grossly, clearly see the principle of Toomey, of Latham, of this now Salter. This is what we're talking about. It's easy to do. Within 2 weeks, you can switch it off. It's precise, and you have to do it in certain regions. So if you went to a North Atlantic or Pacific storm, you're producing about 1% of the salt that's thrown into the atmosphere. But if you do it under one of these stratocumulus clouds, this 24-hour loop here, then it changes the nature of these clouds. And that is what we're talking about. So I think you've all seen this as well. Thank you, Stephen, for this slide. He keeps modifying the design, but these boats aren't really very big, but obviously you've got the Flettner rotors in the middle to actually propel them. And I've included quite a few slides here for actually, so you can look at it, the references, which is always very useful. Top right, you've got Toomey, then you've got Slingo, then you've got John Latham, and I think you can recognize a younger form of Stephen Salter down there. These are some papers. Obviously, well, not obviously, but I've used most of the papers I've been involved with, because then it gives a flavor of what I've been doing. But Wood's been doing it, Gettleman's been doing it. There's a group at University of Washington who've been doing it as well. So there's lots and lots of references, but the basic ones were the Salter and Latham ones. There was another 2008 paper in there, but those aren't it. So now I'm going to move on to how we're getting on with time. All right, Tommy. Now I'm going to get on with the models. I'm going to give some results and then do a summary. So I'm going to focus on the work we did to look at how the random global model, how we did the high resolution models, how it resulted in hurricane weakening, coral bleaching, and the final paper on there is how this affects the meridional heat flux which cools the pole. So this is the first paper. This is what I really want. This was done with a postdoc, and we were basically looking at the reaction of seeding stratus clouds and seeing what the result was. So we took the results from the vocals experiment and we set up the model to run using that data. Great. So it replicated the data. And then on the left-hand side here, we put a small number of what we call low, 42 per centimeter cubed. And you can see that the size of the particles are really quite big, over 50 microns. When we put in a lot of them, which is 380, you can see it's green here. So you're getting a lot of small particles, a lot of small droplets, I should say, putting particles in. And the important thing about these stratocumulus is these circulations underneath. And we're pushing it a bit here. If you put too big a droplets in, it precipitates out and destroys the cloud. If you put so you really must be careful on the size you choose. And that, I think it's about 0.8 microns diameter. But Stephen and I really think we can home in and do better. And if you want to look at it with time, this is low, medium, high. You can see the albedo with the number goes up, and the albedo goes up higher than the medium and the low. You can see the effect on the clouds. Now, I don't want you to take any of that information in really, but it's all in the paper, and I thought you should include it. So that was the first thing we'd done. The second thing, and this is this paper I talked about 2012 with a lot of people on there, including Phil Rash. And in it, we took an atmospheric model. And these green bits here are the only areas that we seeded because we could guarantee you get high stratocumulus decks. We also did the experiment where we seeded all over the globe. And that's what Danny Rosenfeld wants, because he wants to seed. And even if there's no clouds, it will increase the radiation going back. But we said, look, let's do this. So A is 3 most populous regions, and it's only 5% of the ocean surface. And on the right, it's over. And I'm going to now show you some climate model results. So this you can see here are the 3 regions that we seeded, right? And we did it so that by the time we got up to 2040, we somehow stopped the increase in CO2, which we estimated was by the time that the world might actually wake up. So you can see the pictures there. You can see how this reduces. This is the change in delta F, watts per meter squared, and we changed the forcing here. Now, people say, oh, well, that's somewhere, that's a specific location. But the atmosphere's role, remember, is to take heat from the equator to the pole. And that is what it does. I've given you details there. I'm not going to talk about it because it's 2045, because that's details you can look at later if you want to. So here we're going to now look at what we call the hurricane development area. So ran it to 2045, then left it to go a bit longer. What happened to the sea surface temperatures? We were very, very confident that this is an underestimation of what is actually going to happen. And you can see temperature rises of +1 there. When we put double CO2, and you can see these and these double CO2 and these regions where we seeded, what happened to this area? It returned to the pre-industrial levels. So really, not pre-industrial, to the levels we started at the turn of the century. So what we've got here is although we only applied it in those areas, it actually had a huge effect. And remember, the hurricane theory, well, you may not know, is that you can't really get, the argument is you can't really get a category 5 hurricane. And a colleague of mine at NCAS did the research, and he did some research on a hurricane with Kerry Emanuel, and they showed that you're not going to get more hurricanes, but what you're going to do, your category 2 hurricanes are going to become 3, 4, or 5. And that is what's going to happen. So this, even our limited work, showed that it affected the hurricanes. Now, this is the same experiment, just with the 3 areas of seeding, double CO2, and you can see near the poles, it's quite warm. These are the areas for coral reef. And what happens is, just go back, there's Joni Kleinpass. She was the first person to talk about coral bleaching. And remember, it's the spikes, it's the delta functions. And what happened is that when we did the 3 region seeding with double CO2, it compensated for it. And these bleached areas, which are now probably on the verge of disappearing anyway, and there's some numbers there that you can look at, but I don't really want to talk about. But I wanted them in there so you could look at them later. So we did a paper on what is actually happening when you do this 3 region seeding. 3 regions, remember, because we could guarantee a whole year. And the way it does, the meridional heat flux is that atmosphere just takes heat from the equator to the pole. That's what its role is in my terms. I'm a dynamical meteorologist. The atmosphere is there just to move heat around. It does other things as well, but it just does. And if you look carefully, you look at double CO2, you see it's a green line. And this one is if we seed the whole area of the sea surface. And the reason it's really done like this is because you have to integrate from one end latitude to the other latitude. So this is the equator. So what you see is that the blue and the green, the blue and the red, which is you've got double CO2 red, blue is double the control is the blue one. The double CO2 is the green one, and the red one is the double CO2 with the marine cloud brightening, just in those areas. And this one, well, in this one, we've got all the seas, and in fact, I think the ice age comes back to visit Stephen in Scotland. So that is the effect of it, and that's exactly what the Israeli cloud physicist argued, that it was that we should be doing it everywhere. But anyway, so final stage now on this talk really is we haven't done this, so this is the second part. We divided the globe into the oceans part of the globe, 89 areas. We applied, we switched it on and off. I'm not going to talk about that. If you want to know about it, Stephen will explain it more easily. So what we wanted to do was to look where we switched on and off this seeding, what effects. One of the concerns was the Amazon basin. So we looked at those areas, and you can see that seeding in those areas affected the change in precipitation. And we looked at the northern area of there. So you're going to have consequences, and I've got a slide later on the effect of precipitation. There's going to be consequences of seeding, not as much consequences as double CO2, mind you, but it would give you a helping hand to decide where you're going to put the seeding structures. So really what I'm saying is, and this is discussion really, net zero is necessary, but China, India, it's going to be pointless, because we're already, there's another 40 to 100% increase in CO2. And I'm not worried about the CO2 or the water vapor, but that's a side effect. Marine cloud brightening is cost effective. You give a good Messi's salary for 5 years and we could do all the work. And then, well, it doesn't take many $1 billion to actually build these ships. It can be switched off. And that was in the third paragraph. And the overall, it's a plan B. But now, I think we're on to plan B, because plan A, removing the carbon, is not likely. So in this talk, and I've gone very quickly, is what I've tried to do is give some idea of the data. So I've given you the data, the observations. The frightening thing is what's happened to the sea surface temperatures this year. Now, it could be a one-off, it could be a dynamical effect of the Azores High, but why was it all over the Northern Hemisphere? It's certainly, the El Nino can't be there. You can't, the Azores High, and you can't talk about Saharan dust affecting the whole globe. The second thing is I've given you a background to the physics. What is it we're looking at? We're looking at CO2, we're looking at methane, but the big effect is water vapor. And if you argue we remove the CO2, then increases, then it's not, we're still going to have the problem. I presented some high resolution model simulations, and other people have done it as well. So there's a lot of discussion. I've presented some high resolutions cloud simulations. People like Feingold and Wood have done some. There's a lot of discussion about how it will work, how it does work, what does it do, the microphysics arguments. But I think the theoretical arguments are still there. I showed the effects on the meridional heat flux. That is what is melting the poles. People talk about Arctic amplification. I hate to tell you, it's the fraction of a petawatt of the warm air. Every time you have this warm air outburst going up the east coast of the US seaboard, that I look at the charts, 500 millibar, halfway up the atmosphere, and I think, oh my goodness, it's going to be melting more of the Arctic ice. I predict that by 2035, in September, there'll be no Arctic ice at the North Pole. By no, I mean less than 15%. And even people like Slingo, Julius Slingo, and Graham Stevens, I think they would agree. And I've talked about hurricane weakening and coral bleaching. I also talked about this coding manipulation, which is needed as well. If you're going to try and focus the efforts. My original work was just to look at those three areas. But there's as Stephen said this yesterday, we need to optimize the salt. I think what we've decided would work. It needs to be monodispersed. That's absolutely incredibly important. But if we can get a 10-20% more efficient by choosing the relative optimum size of the sea spray, salt spray, using the high resolution models, that's good. And we need to apply that. So in reality, is the planet being cooked? Yes. Pessimist? Yes. Trump supporters? Well, global warming doesn't exist. I think the optimists, can we do it quickly? Yes. But we have to now reduce solar input by marine cloud brightening. That's the best option for me. I can show you that. I've got a slide later on, have a look at it if you like, which shows the effect of not Krakatoa, the recent hurricane. And it's once you put those aerosols up there in the stratosphere, what worries me is it affects the ozone layer, it affects the ozone hole, and it also doesn't cool the poles down very much. Carbon dioxide is going to increase, and if you're a pessimist, it's the end of the Anthropocene. But that is what I want to say, really. I hope I haven't gone too fast or given too much technical information, but it's about 40 minutes. Okay. Thank you.
Thank you, Alan. That was excellent. That was really excellent. Do you want to maybe remove your slide so we can see each other here?
Yes. Has that done it?
Yep. Yeah. Thank you. So we will now have a question and answer period. And as I said, Alan hopefully will be able to stay until about 6 my time. So we have a good, 49 minutes or so. And please just, put your hand up if you want to ask a question. I'll try and keep track of the order here. And I see that Clive has his hand up. It's the first question to Alan.
Okay. Thank you very much for that, Alan. That's very good news to see all that. I couldn't say I understood most of it, but it's very much in line with what we've been, the conclusions we've been coming to ourselves, many of us here, because we have all these other meetings. I've got kind of two questions. Stephen Salter already knows that me and another gentleman who's not here tonight are proposing, if there's any problem with getting monodispersed sea salt particles, droplets, you can easily make aerosol particles using chemistry. The military have been doing it for over 100 years to obscure their operations. They make some stuff anyway, so we don't want to do it quite the same way as them, but we have all kinds of ideas. And once the cloud burns off, it photocatalytically removes methane and black carbon aerosol. It makes black carbon aerosol more hydrophilic, so it rains out better, and it can also remove high concentrations of tropospheric ozone as well. So do you see a role? Do you see a use? Does that sound interesting to you? Stephen's here, and he's very helpfully actually offered help with a spray tunnel to us for doing this. How does it land for you, Alan?
The reason I want it monodispersed is because I've seen the effects off the coast of Chile of having larger particles and smaller particles. And the smaller particles just make a haze, remove it. And the larger particles, if you like, nappy powder, that was tried off Florida and worked tremendously well. You want to remove them. So I've attacked it as a microphysicist, a cloud microphysicist, and it is of interest. But I know that the cloud seeding to get rain is very dubious, but I know if you fly above a paper mill, for example, you will precipitate out the rain. And my concern all the time is to maximize the change in albedo. So I could comment on what you've said, but I'm really not an expert on some of these other facts. Stephen probably knows more, but it worries me that if we don't get this right, then you could have a sort of cloud dimming process, which is what happened off the coast of Chile when they turned the smelters on, that you actually got rid of the cloud by having far too many it just became a haze. So I'm not answering your question, I'm sorry about that, but I know from the cloud microphysics point of view and the equations that if you do it too big or too small, you reduce the efficiency of it. But on the other hand, you could see that even those small areas, doing those small areas would combat double CO2.
Yeah. Okay. I mean, we definitely don't want to do it if it's going to make it worse. We understand that the albedo, the need for increased albedo to reflect more sunshine away. So if we can't get the right size, then we just close up shop, basically.
We wanted to do some experiments with aircraft and just to check that I want Stephen to produce a few different sizes, and so we can actually check. And the other thing from a microphysics point of view, it may not be the optimum size in all parts of the globe for the different types of stratocumulus cloud. So there is a question. Those regions are subtropical stratocumulus, and they're quite similar. So that's why I was choosing it, really out of naivety or simplicity, because it's really quite complicated.
Yeah, I mean, we think that we use hot vapors and we mix them up. We can get the right size. Can I just ask my other question, or shall I come back later if you like?
Maybe come back later, Clive. Thank you. Yeah,
okay.
yeah.
Okay.
We usually are. We have, you could have a follow up. Maybe one follow up, and then we try and move it on, and then just you get it back in the queue. Thank you, Clive, and Alan, of course. Robert Tulip.
Thanks, Alan. Just magnificent. Really appreciate it. It's a very compelling story that you've presented about the urgency and the need for this work and the simplicity of it. I just wanted to add, for the benefit of those attending, that we're working together with Stephen Salter to seek the initial minimum viable project, I suppose, for how we can get this work underway. And we suggest that an investment of about $5 million is needed to continue your work on modeling with Leeds University to prove the engineering problem of this sub-micron monodisperse salt aerosol spray. It's a non-trivial problem, being able to generate a salt aerosol that's smaller than a micron. And Stephen's workshop in Edinburgh is ready to do the work, just with a really small amount of funding in terms of the security impact of global warming. So we've got the proposal pretty well ready. We're getting our rebrighten.org website, which will be able to provide some of this information. And so the challenge is identifying people who are willing and able to provide funding to get this work done, and also to help us get this message out. It's such a challenge that there's such strong and really quite crazy political opposition to doing this basic research into how we can actually address the global warming problem. So I really just wanted to thank you, Alan, for sharing that basic science with us. And if you have any comment on this practical process of taking it forward, I would welcome that.
I think you're exactly, well, you're right about the way to go forward. I would like to see 2 or 3 different groups maybe doing some of the modelling. We've done some of the modelling already, preliminary modelling, and now we just want to home in it. But I'd love someone else to do the results. When we were talking about Graham Feingold's work, he did it on ship tracks, and they were brighter, but the ships were also pumping out a lot of large particles, which actually dissolve some of the things. So yeah, but I think coming back to your comment is that, yeah, I think that's the way to go. The technology, if you had to say 0.8 now, this is my diameter, whatever, I would say go with it, because I know it'll work, but it might be better 0.7 or 0.9 or something. I think it's about 0.7. Or sorry, we're talking radius and diameters here, and wet and dry. So I don't want to confuse them. But yeah, I agree with you. Yeah.
And just to follow up on the modelling, it's surprising that there are a lot of scientific papers that question the efficacy of marine cloud brightening, but generally they seem to apply quite unrealistic parameters to the deployment strategy. Could you comment on that, Alan?
I think that's common in a lot of science, actually. There's always people, I mean, this theoretically, if you look on the slides later on, you'll see a slide by a man called Charney, and he had a very analytical computer model with gigatons, and he's done better than most climate models. He was a brilliant dynamical meteorologist from MIT, and he's done as well, and he's actually predicted what the warming would be for the emission of so much carbon. So, but he was lambasted, and people still argue against it. But until it's actually repeated several times and tested, and that's what we've got to do, test it. And there'll always be different people saying not David Keith, but the people who promote stratospheric sulfur, for example. They will always try and find reasons. And I don't understand it, because in many ways we possibly might need both techniques, but I don't know. But the marine cloud brightening, I'm convinced, will work, especially after this summer.
Thank you, Clive. Clifford.
Yeah, Illinois.
Clifford, would you mind introducing yourself? Because I don't believe I've. Yes, please. And if you are interested, please sign up for our to be in our Google group if you want to get more notices about these kinds of presentations. But go ahead, please.
Yeah, I've been an author on a few of these papers. I work on energy and sustainability engineering at the University of Illinois, and we're doing some integrated assessments modeling, and so this caught my eye. That includes with and without SRM. And there was a paper by Claudel that was submitted to Environmental Research Communications about mono size, very small dispersion size salt particles made with ethanol water mixes. And it's just been submitted, so I don't know if it's penetrated yet, but I wonder if you had a look at it or you know about the idea anyway. These are much smaller. Well, this is dry weight, so they're much smaller particles than you were talking about.
No, I'm afraid I haven't seen it or heard about it. The problem is that I come back to this. I'm a cloud microphysicist, and we have certain equations, and these equations might underestimate. So certain people like Armand Newcomb's, he made the inkjets, and he was working on much smaller size. I'm right there, Stephen, I think, much smaller size. and he was using the inkjet spray, and I'm afraid he's not very well, and he's not continuing now. But I just look at the equations, look at what Slingo did, and then put it into a numerical model. Now, I'm very cautious about numerical models. So one of the things we could do is put smaller particles in the numerical model. But when we did that, I showed you the work of Andreychuk there on the model there. And when we put small aerosol in, it wasn't very effective at all. However, I have to say that this was 2 dimensions. So you're not getting a 3-dimensionality. And there's a big difference between 2-dimensional clouds and 3-dimensional clouds. So I can't say definitely, but I worry about small particles going in. And sorry, I haven't seen your production with methanol or whatever.
Not mine. This is people from Texas.
You're the one you were talking about. So I'm sort of blinkered in what I know will work, and other things may work. So that's the problem you've got with me.
Okay, yeah, you're talking about salt water, and they're talking about salt itself. So maybe there's some confusion there.
Well, yeah. I mean, it's dry and wet. Yeah.
Okay, thank you.
Thank you, Clifford. Before we move on, Alan, I just had a kind of a layperson's question. So stratocumulus, is that the same thing as a marine cloud? Because I mean, there is the cirrus cloud thinning. They talk about cumulus clouds, so those are higher up, right?
Yeah. Sorry, stratocumulus. Stratus means a layer. Cumulus means the white fluffy clouds, and they occur, maybe depend on the part of globe you are. They may occur anywhere between 500 or 600 meters and maybe 1,500 meters, because meteorologists tend to use that. They occur over land as well, but over land, the air is so dirty that you don't tend to get them. And it's one of those properties like lightning. Lightning doesn't really occur over the sea, although it does because of the drops, the sizes. But the marine stratocumulus is what we should really be talking about, over the sea, layer clouds, thin layer clouds, that if you're flying over the top in an aeroplane, as one does, there's just this layer of sort of rolls, the continuous layer. That's the stuff I'm talking about. And it's not a simple, these naive questions are the hardest to answer.
Yep. Thank you for that clarification. Jonathan.
Yes, thanks. That was a great presentation. So my question is, the diesel smokestacks of shipping are putting out an enormous variety of particle sizes. And the recent scrubbing of the compounds that were deemed to be bad pollution has led to this dramatic increase in sea surface temperature, maybe even as much as 0.5 degrees Celsius. So this simple action of scrubbing either their fuel or their emissions has resulted in the removal of a whole lot of marine cloud brightening. This seems like a very crude, careless thing that certainly doesn't focus on 0.8 micron or below particles. Have you studied, or can you say something about the type of particles that have been removed by this scrubbing and why they've been so effective in allowing the energy of the sun to reach the water surface?
Right, I really can't comment on that, but if you put aerosols of any size into a dry boundary layer, what the result is that you will reflect the incoming solar radiation. So if you looked, I don't know, volcanoes go off and they produce these horizontal glass plates at maybe 2 or 3, 4 kilometers, and they stay there and they reflect a lot of radiation. When you get the sulfates coming out of the ship's sulfur and it converts to sulfates, these are often sort of horizontal plate-like crystals. So I really don't know what they've done or what they've taken out. But if you look at the papers about aerosol content, they've been predicting this for years. And it's obviously cleared up the quality of, we can go to the average port, even the US anywhere, and you'll see that the air quality is so much better. Obviously the soot falls out, but the aerosol will any aerosol will reflect radiation. That is distinct from how it affects the clouds. So near the land, whatever you pump out is not going to affect these stratocumulus clouds because there's so much coming out. There's so much. If you look at Australia, you can see it hidden by this haze of particles caused by all the mining for all the metals and the coal and things going to China. That is reflecting solar radiation. So really, I cannot answer the specific question, but yeah, there's people arguing we should be pumping out sea salt or something to cool the planet down. And yeah, maybe we should, but that would certainly cool it down. But there are consequences.
Right. Well, my one follow-up then is, if it was a simple matter of scrubbing the emissions or the fuel of the ships in order to cause a 0.5 degrees Celsius temperature change, it would seem like doing the reverse, somehow adding sulfur or whatever compounds for the actions on the open ocean, where they're not near a port and they're not creating a polluted port, would seem like a way to create a 0.5 degrees Celsius in the other direction. And
well, this is Stephen's argument, I think, that you could do it by basically just putting sea salt, just spraying sea salt into the behind the ship, and if it's in an area where there's a storm, it'll make absolutely no difference. It's only in these calm regimes where the air is still, and that's quite often in subtropics, where you could do this. And as I say, this is what he's written many papers in Science about this with Feingold, saying that we really need to increase the aerosol in the lower atmosphere. But I don't think, from the radiative calculations, it's as effective as marine cloud brightening. But that is because you're going to have to spend a lot more effort doing it. But maybe Stephen's got a comment on that, because I know he's thought.
Stephen, did you want to? We have a group. Actually, Jonathan, you might want to contact me. We're trying to work up a proposal along the lines that you've discussed, and Stephen has commented on that. There's a thread in I think it's in geoengineering and some of the other. But just contact me. But you know, as just an emergency immediate measure, it appears that one could just relax the regulation for the out in the ocean. But much better would be, of course, to have some kind of benign aerosol, and Stephen has suggested. Steve, did you want to comment on that? Stephen, you suggested just spray salt water in the.
Yeah, you could. Well, yes, you could inject salt into the exhaust manifold of a marine diesel engine, and there's lots of other gases going up, and that would move the salt particles up to where they'll mix in the clouds, and it would do the job. And that would be a very, very cheap thing to do. The only disadvantage of it is that the ships go where the ship owners want them to go, and you might decide it would be better to go somewhere else. And in fact, the places that we probably want to go is where the shipping is very low. The places you've looked in the Pacific, there was not very high shipping density. But we certainly could do that. It's a bit of a distraction from being able to do it where we choose to do it, and to stop when we don't want it. So the other point is that to see a ship track, you need to get a contrast change of 40%. Well, you can't tell at all if it's less than 15%, but a nice bright ship track is probably 50 or 60% contrast change. So it's an enormously much more than we want. We want to do a gentle increase of perhaps 5% if you could do it in just 10% of the world's oceans. The problem is actually only about 0.5%. If you could do it everywhere, just a 0.5% increase in reflectivity would solve the thermal problem.
Right. So thank you, Stephen. I think the data that the latest paper that I've looked at estimates that over the shipping lanes, the major shipping lanes, about 1 watt per meter effect, but with a global impact of about 0.1. So it wouldn't be ideal. It wouldn't be like Marine Cloud Brightening, but it would be a quick way to implement this on a fairly. So anyway, that's because the question becomes implementation while we're building the Salter yachts or the Vito yachts or whatever. I'm sorry, that's Hartford who has to leave. But and it would serve the function of raising the issue, very clearly that the aerosols and marine cloud brightening and other techniques are significant and important, and we should be thinking about them. But I'll move on to Herb.
Thanks, Ron, and thanks, Alan. That was really provocative. And as much as I consider myself a sort of doomer in many respects, watching the first few slides added to that. And of course, you then reversed it at least a little bit with the rest of your presentation. Some of you may know I recently wrote a book called A Climate Vocabulary of the Future, and I have a write-up on MCB, and I coined the term designer salts to reflect the fact that we're talking about a designed salt, not a natural salt. I'm intrigued with not just so intrigued, but I'd really love to know more about what do you mean by temporary? In other words, flesh that out in terms of why MCB would only be looked at as temporary, whether it's temporary and temporally or spatially or otherwise. And I guess the last thought that came to mind was, it sort of reminded me, if we're up at, God forbid, at 3 or 4 degrees, and somehow we're still able to even manufacture and maintain the ships that produce the and disseminate the salt. It sort of reminds me of the analogy with being on a kind of heart-lung machine. If you're in the hospital and you're almost incapacitated, and this sort of takes over the breathing and the respiration and the metabolism for you, that we would become so dependent on this, if and until we were able to pull the carbon dioxide out of the atmosphere and eliminate our emissions. But that said, tell us more about temporary and how far can you stretch temporary to be close to permanent?
Well, by temporary, in the terminology I've got, I'm talking about 50 or 100 years, because, and I keep coming back to this, you were talking about 3 or 4 degrees warming. I can't see if you look at the amount of carbon dioxide that China and India are planning to pump into the atmosphere, that 4 degrees is pie in the sky. You're talking about 6 or 7 degrees. That's right. No, seriously, there is no way that it will not. Now, the way I say temporary is because eventually people will realize this is happening. Removing CO2 is not an easy operation. I don't think it's an easy operation. No one has done it. So temporary, I'm going 100 years. If it's not solved within 100 years, then I sit on this regulator panel, and I'm telling them they're going to have to cope with temperatures that are at least, by the end of the century, at least 4 degrees warmer. And what's actually happening now in France, they've got all these nuclear power stations. In 2018, they switched 6 of them off because the control rooms overheated. That's why I mentioned the computers, that it is so expensive to cool the control software, the control hardware, that they had to switch the power off. And it was a bit embarrassing because Britain was using coal to send to France for electricity. So temporary is, to me, in terms of, if you look at the Younger Dryas, sorry, it's an event that happened 12,000 years ago, and the temperature suddenly shifted, and it went down and then it went back up, and it was to do with the marine circulation as well. And that was a temporary event that lasted about 100, 150 years. And I would say that we're talking about, this could continue. If you believe Danny Rosenfeld, then we're all right for CO2. But when the temperature gets up, and that's why I put that 6th slide in there, when the temperature goes up, I'm not worried about CO2, I'm worried about water vapor. You're going to have to extract the water, and that's because the water vapor will totally, at 6 degrees, the water vapor will dominate anything we do with CO2. And remember, you've got to get the water vapor out, and you can't if the temperature's hot.
So what would, so that's a different conception of temporary than I had in my mind of 50 or 100 years, which is much more reassuring. So if you were, if we were meeting 20 years from now, and the temperatures continued to rise as they had been, but MCB started to be applied and deployed, let's say a decade from now, at the kind of maximum feasible capacity, and everything goes right, what would life be like in 20 years vis-a-vis the climate, with the temperatures increasing and MCB at full throttle? I don't hear you.
Alan, you're muted.
If you had MCB at full throttle, I think you could bring the Ice Age back. I really think it's that effective. That's what the model result
at the appropriate throttle then.
Okay, I think you could maintain it, but the problem is CO2 is going up. So you've got this background CO2 rising, but the compounded effect of warm air, warm temperatures, means water vapor goes up. And you've got the added complication, because I'm afraid New York's going to be, London are going to be underwater. Holland is already anticipating that. If we don't do it, then the local regions. And when I gave a talk in Washington about 10 years ago, there were 2 guys from the Pentagon there. And I said, why are you here? He said, we're looking for areas that could cause instability, and climate change is one of them. And they said, why are the British worried? And I said, well, there's 200 million Bangladeshis with British passports that could come. There's going to be mass migration. So I think you're going to see mass migrations, because remember, if you look at 50% of the world's food, it comes from less than 10 meters above sea level.
But what if I could, I'm a little confused. If MCB is working optimally, and it could bring presumably temperatures back to what they are now, or even what they were, in mid 20th century, or whatever the world shows. So wouldn't that minimize or slow down sea level rise and minimize the increase in water vapor?
Well, you've got the problem of Greenland. Greenland only exists as an ice cap because it's so high. So you now have reduced the height of the ice at Greenland, and you're going to have to do something very, very severe to stop it melting further. Even even if it wasn't, even if the planet wasn't warming up, if you take the top few hundred meters off the Greenland ice cap, you have a major problem, because it only exists because the ice only exists there because it's so high. So there's some interesting oceanographic papers and ice papers on the formation of ice, of what is going to happen. So if you look at the Arctic melts. Well, it doesn't really matter. It's like your gin and tonic. The ice melts. It doesn't go over the top. But if you melt Greenland and you melt Antarctica, that's on solid land, then the sea level rises. And remember, 50% of sea level rise is predicted to come from just thermal expansion. So yes, we can cool the planet down, and yes, we can do it, but we've got to do something to address the melting of the ice caps. You could reform Antarctica, yep, that's fine, but Greenland is a problem, and that's 7 meters. But that you're talking of there, probably about 100, 200 years, but it will happen.
Thank you, Alan. Yeah, if I could just, there's the issue of the modeling that shows the heat will come back out of the ocean, and the temperature will stay put even as the greenhouse gases are falling out, so that the cooling could it kind of, I think, further makes your point that we may need cooling for many years in the future, even if we are successful in drawing down greenhouse gases based on that modeling. But let me go to Kevin.
Hi, Ron. I think you've almost answered the question, or the point I was going to make was, when we're looking at cooling interventions, we need to think clearly about the specification for it. And the large part of that is how long that the cooling process must go on. And when you look at the Vostok ice core and extrapolate from that, it will take something like 200,000 years for CO2 to return back to stable conditions. So it seems to me that the cooling that we need to introduce needs to be indefinite, 50 years, 100 years, 200 years, and not the sort of time scales that we need to be thinking of. We need to be thinking of a cooling intervention that we can sustain for in the order of 100,000 years, basically forever. And that's just what it is. As Alan says, there's been no quick ways, or there's no quick ways on the horizon at all for getting CO2 out the atmosphere quick enough and overcoming all the hysteresis problems that we've got in the climate system. So we have to be looking at the uber long term for climate intervention and for climate cooling. And I think when you look at it in that perspective, of really thinking what the specification is, that then starts driving the engineering solutions that we have in front of us. And allied to that is that in the coming years, if we want to try and tackle climate change, we have to cut CO2. Therefore, we have to massively reduce energy consumption, which is basically will drive some major economic collapse. So as part of the specification, we need cooling that can last for effectively for the rest of civilization at a time when there's minimal energy to operate it. And it does seem to me that MCB is one of the few candidates that can tick those boxes.
Kevin, I'm sorry. Go ahead, Galen.
Can I comment on that? I
Sure.
think fusion reactions will occur within the next 20 years. I think that solar introduction of great solar farms could provide masses of energy. So I'm really quite confident on the energy front that in 20, 30 years, it'll be all right. But coming back to the previous comment, when you looked at the bomb tests in the 50s, what it showed was the oceans have got a typical life cycle of 300-400 years. So in terms of the warming that we're doing to the oceans now, the deep currents, we've got a little bit more time than many people would expect. Liss at University of East Anglia and several Europeans did that. So I'm not quite as pessimistic as you. But if India increases, if China and India keep producing more CO2, then you're in a hiding to.
Yeah, I'm much less confident than you are on that one, Alan. You know, fusion. You know, the standard joke is it's always 50 years away. And even if we got fusion working and solar and everything else, we still got this legacy of a huge amount of CO2 in the atmosphere, which is not going to disappear anytime soon at all. Even if we can double, you know, the CO2 uptake in the planet, we'll reduce the time period from 200,000 years to 100,000 years. In whatever way we look at it, for all the things that you have talked about, we need to be looking in time periods of a minimum, so it's 10,000 years. You know, it's nothing on the horizon I can see is going to stop the rapid sea level rise. And again, coming back to what you were saying before, Alan, that we get the sea level rise, we take out a huge amount of agricultural land. But what we'll also do is flood nuclear power stations, oil refineries, ports, military installations. I mean, something like 50-60% of the whole global economy is within a couple of meters of sea level rise. So it's an insurmountable problem that we've got at the moment.
I might jump in, and I think that the problem is surmountable, but that by increasing planetary albedo, we can address the temperature problem quickly enough to prevent the dangerous sea level rise. So what I would like to ask is, one of the problems with the solar geoengineering is the observation that it would disrupt weather patterns, for example, the monsoon. And so I'm just wondering, Alan, if there was a combination of a very low dose of stratospheric aerosol injection together with targeted marine cloud brightening that could address some of these problems, like the monsoon, like the El Nino, the Indian Ocean dipole, like Atlantic hurricanes. That sort of combined approach would work to prevent the dangerous sea level rise and temperature rise. Does that make sense to you?
Yeah, it does. I mean, I've always thought, and John Latham thought, that we're pushing marine cloud brightening, but I think we're going to have to consider everything possible, to be honest. If you look at the slide a bit later on, it shows the change in precipitation patterns with double CO2 and the marine cloud brightening, and there are some big precipitation patterns changes. So yeah, I think I agree with you that I'm not as pessimistic as you are, Kevin. I mean, I think there are things we can do. Well, I hope I'm not as pessimistic. Maybe I'm, but I agree. I agree
sorry,
with you, Robert.
When I said insurmountable at the end, I think and Robert's you're probably correct to me. We absolutely have to do this. We have to cling on to this and absolutely go at it at full pace and think carefully about the specifications. Sorry, back to you, Alan. Sorry.
But if you look at Danny Rosenfeld's comments again, and you marine cloud brightening over the whole ocean, you would actually cool the planet down. And if you cool the planet down enough, then the double CO2 is not that severe at all compared with double CO2 and the warming. Because if you get the warming down, then your agriculture will be, it's the extreme temperatures that kill off agriculture, kill off production and things. And therefore, I think in the end, getting the temperature down is critical. But that probably doesn't answer your question, Robert.
I'm gonna thank you, Alan. We only have about 10 minutes left, and I'd like to make sure that Hartford anyway. I'd like to make sure if I could just call on Stephen, because he's our other Marine Cloud Brightening expert here, and then if we have time, maybe Robert, Chris, I know Clive, if we and the other folks here. And just so everyone understands, the official position of HPAC is, in fact, let's try a lot of different things. We don't want to put all our eggs in one basket. And so anyway, okay. If you don't mind, I'll just call on Stephen. Good, Stephen.
Hi. Well, first of all, the amount of engineering that you need to do to cool the planet with marine cloud brightening is really very small. We might need several hundred or maybe 1,000 vessels, and they displace 90 tons each. So it's a tiny fraction of the world's shipbuilding industry, and we could do that forever if we had to. The second thing is that there's a very interesting paper from the Norwegian Stern, I think you call it, at the Cicero Labs in Norway, where they, instead of blasting away between 30 north and 30 south, which is what nearly all the modelers do, they decided that they would only spray in areas where there were low clouds. This is not actually the most sophisticated tactic that you could have, but it was a nice one. And that showed that there were changes in precipitation. There were increases in almost all the drought-stricken regions. And there were reductions in precipitation, but they were all over the sea. And I've got those maps in a leaflet I've sent around. So there are effects on precipitation, but they're all benign. They're jolly good things to do. We would like to have the increases that are predicted. And I'm sure that the Norwegians could think of an even better strategy than just looking to see whether or not it's cloudy as a choice of where to do the spraying. I think we will be able to have climate planners who will have very high speed satellite data coming down real time, and they can plug different possible cooling patterns into fast operating model predictors, which I think we need to make a lot of improvements in climate modeling, and they would be able to tell us, they would be able to do a merit order of all the ocean regions, and they will tell us that the fleets have to be moved either north or south or wherever to get what the planners think will be the best thing for agriculture or cricket matches or whatever, however you want to control it. We will be able to decide, if we've got clever enough politicians, we'll be able to decide exactly what kind of climate we want, where and when. And I think it needs just a different way of looking at the way we drive the climate rather than let it drive us.
Do you want to comment on that, Alan?
It's a great.
I'd rather hear someone else ask a question or raise it, or see there's still 3 hands up. I can stay another 10 minutes easily.
Okay, great, thank you. Okay, so Stephen, did you have a follow-up, or go ahead?
Yes, one thing that's a bit sad is that John Nissen isn't with us this evening, because he's been very negative about marine cloud brightening, and I hope that he'll watch a repeat of this.
John, yeah, I should say, Steve, that John asked me to do a very quick, rough and ready calculation.
Kevin, yeah, let's go in the queue here. So the next one up, who hasn't spoken yet, would be Robert Chris.
Yeah, it's late in the day. I've got a question which is slightly kind of off the wall, because it's not actually about marine cloud brightening. So what I will do, if I may, Alan, is I will email it to you, and perhaps cover it off there.
Good. Anyone email me anything they like. Yep. Okay, I'll try and respond. But do look at some of the other slides on that PDF that's out.
Will do.
Okay, and now we're back to Clive.
Okay,
and
thank you very much.
Go ahead, Clive.
Thank you, Ron. So it's hugely encouraging, Alan, that you say, well, we could have another ice age if we wanted. But my question is, with Greenland losing altitude and going past its point of no return, we might, use marine cloud brightening to cool down the oceans, but still find that Greenland eventually collapses. Do you think? But the winds, a lot of winds on Greenland, they're katabatic. They come down in the middle and then they go out to the coast. If there were enough aircraft, so this is back to our aerosol that you can stand out of an aircraft. Do you think that whatever it is, some kind of benign aerosol in the summer months? Because I know it's like you can only cool the ice sheet, the polar ice sheets in the summer months, because the rest of the year the clouds trap more heat than they reflect, as I understand it. Do you think there might be enough cooling in the summer months to just maybe allow to preserve the winter snowfall, to maybe allow the ice sheet to come back up again?
I'm not. Oh, just a minute. I'm not sure that it will come back up, but I'd look at it a slightly different way, and I think you could ask. Jane Francis the same question. I think it will reform over Antarctica. The water will condense somewhere else and the ice will form somewhere else. So maybe Greenland going isn't as disastrous as all that, because the planetary system will, and if you look at Mars, the ice caps move from one end of the planet to the other every 2 years or every solar year. So yeah, Greenland going will raise the sea levels,